Hi, it's Moser with a quick tutorial on covalent bonds and molecular compounds. After watching this video, you should be able to identify molecular compounds as those which are made up of atoms that are bonded covalently. You should be able to explain the forces that cause covalent bonds to form in a given position, and be able to differentiate between single, double, and triple bonds, both in terms of the electrons shared as well as in terms of bond energy. You should already know what a covalent bond is. If you're unsure, go back and review those videos. And you should also already be aware that higher energy atoms are less stable. With that, let's get going. So to start off with, we should define the molecule. A molecule is a neutral group of atoms which are held together by covalent bonds. In other words, a group of atoms that are sharing electrons with one another, but that overall form a unit which is electrically neutral. So when we talk about compounds that are made up of molecules, we often call them molecular compounds. And these include things like water, H2O, ammonia, NH3, and this crazy thing, well, it's some sort of oil, but it's made up of all things that are sharing electrons. If we look at any of these compounds, a molecule of any of them overall, we'll find that we have the same number of protons and electrons, making each molecule electrically neutral. What does this mean? It means that when we have a beaker full of water, for instance, we really have an entire collection of discrete pieces. And this is going to become very important when we start to compare molecular and ionic compounds. But the forces inside this little molecule are pretty powerful. The forces that hold one molecule to another are less so. But the important thing to remember is that in a molecular compound, we have discrete units called molecules. That's going to be really important. The nice thing about these discrete units called molecules is that, boy, it makes formula writing really easy. Because for any substance, ionic or molecular, we can write a chemical formula that gives us the relative number of types of atoms in a compound. For molecular formulas, it's an exact formula. It's an exact recipe for a single molecule. So the molecular formula, which is what we call a chemical formula for a molecular compound, gives us the type and numbers of atoms in a single molecule. So, for example, water, H2O. Well, there are 2 hydrogens, 1 oxygen. Couldn't be much easier. In diatomic molecules, such as O2, N2, there are a whole bunch of them, we know that there are 2 atoms of oxygen bound together. Let's just make sure that we're clear on these molecular formulas. So this is a formula for a molecule of glucose, C6H12O6, and you've probably seen this before. It's something we talk a lot about in biology. This formula contains a couple kinds of pieces of really important information. The first are these chemical symbols, C, H, and O, which tells us that this molecule, every molecule of glucose, is made up of carbon, hydrogen, and oxygen. The next important piece of information are the subscripts, and these tell us the exact number of each type of atom that comprises a single molecule of a molecular formula. Okay, now let's talk a little bit about how those covalent bonds form. Well, it's a dance. A dance? Yeah. It's a balancing act between the attraction of protons and electrons for one another and the repulsion that protons exert on other protons and electrons exert on other electrons. Kind of awkward. Maybe not as awkward as this, but still. What we have is a situation where the protons and electrons are rushing towards one another, pulled by that electromagnetic attraction. But they run up against the wall of the repulsion of the electrons in one atom for the electrons in another, as well as the repulsion of the protons in one atom for the repulsion of the protons in another. What happens is that this gets balanced out. It's kind of like this. There's that adorable person who you've known your whole life. They're so cute. They're wonderful. Ah, cutie pie. And the minute you see them, you're attracted to them. You race towards them. Unfortunately, cutie pie has a really objectionable best friend. Best friend. Ugh. So, just as you're approaching cutie pie, ready to dance your dreams into being, yeah, there's best friend. So, this is what sort of stops that race of attraction and settles us out at a distance that minimizes the energy. Oh, wait, there's that energy thing again. Hold on. So remember that atoms in their unbonded state are very often unstable because they don't have that ideal arrangement of electrons, that octet, or a full upper S&P. So here we get the example of two hydrogen atoms, and while those electrons are repelling one another and those protons are repelling one another, the effect of the protons in one atom to the protons in the other is to pull them strongly together. But still, unbound, they're not stable. Well, what if we move them a little closer? We can move them to a point where their energy is at the lowest possible. In other words, the attraction and repulsion are balanced. This is a stable condition. Well, what would happen if the attraction for cutie pie overcame all good sense and the repulsion of the like charges, and those atoms pushed closer together? Well, their energy would go back up, because now the repulsive forces of the protons for the protons and the electrons for the electrons would be pushing them back away. It's kind of like the second hill of a roller coaster. That repulsive force would push them right up to the next hill. You want the lowest possible energy level because this is your stable position. That's the distance where bonds form. So if they're too far apart, they're high energy. If they're too close, they're high energy. What you want is that perfect distance where their energy is at the lowest possible point. In other words, they're the most stable. This is where we get into the conversation about bond length. And bond length is very simply the distance between the atomic nuclei in two bonded atoms. Bond energy is the difference between the potential energy of the two unstable, unbonded atoms and that low energy condition of the bonded atoms. So, this chart, which is reproduced from your Holt chemistry textbook, shows two atoms that are too close, two atoms that are too far, and this nice low energy stable condition of atoms being just the right distance apart. The difference between this energy and this energy ends up being contained inside that bond. So when the two atoms bond, energy is given off. And if you want to break that bond, you're actually going to need to input some energy to do that. Now, we'll talk more about bond energy a little later. What's really interesting is that some atoms can, and do, share more than one pair of electrons. So when atoms share one pair of electrons, we call that a single covalent bond. When they share two pairs of electrons, that's a double bond. And it probably doesn't take a rocket scientist to figure out that a triple bond is when two atoms are sharing three pairs of electrons. So the interesting thing is that multiple bonds tend to be shorter and have much higher bond energy than single bonds. If you've got access to a rubber band at this point, go ahead and grab it. Let's do a little metaphor. So what we've got here is my two fingers representing two atoms, imperfectly at that, and that rubber band, the bond between them, representing a single shared pair of electrons. So if you've got a rubber band handy, you can do this. And it doesn't take it takes almost no energy for me to stretch the rubber band to that degree. It's easy. It's not stretched very tightly. There's not a whole lot of energy stored in that rubber band at that degree of stretch. Now let's try something. Double your rubber band. Now here I've doubled the rubber band, and as you can see, my finger and thumb are a whole lot closer than they were. And it's taking me some energy to stretch that rubber band. In other words, there's a lot more energy contained in that little stretched rubber band than there was when it was single. Now, if you've got your rubber band, try to triple it. It's an imperfect metaphor, but you can see that with the rubber band tripled, I can barely separate my fingers. It takes a tremendous amount of energy to separate my finger and my thumb because there's a lot of energy contained in that tightly stretched rubber band. Likewise, single bonds tend to have lower energy contained in them than double bonds, which tend to have lower energy contained in them than triple bonds. Put another way, single bonds have less energy than doubles, doubles have less energy than triples. Or, to put it yet one more way, when we look at the energy in unbonded atoms compared to the energy in single bonds, double bonds, or triple bonds, we find that the energy contained is lowest in the triple bond, while the energy contained in the single bond is the highest, though it's obviously lower than an unpaired atom. Okay, can you identify that a molecular compound is made up of covalently bonded atoms? Hopefully yes. Can you explain why covalent bonds form where they do, in the position that gives the overall atoms the lowest possible energy and therefore the most stability? Can you differentiate single, double, and triple bonds as things that share 1, 2, and 3 pairs of electrons respectively, and that single bonds have less energy contained in them than double, which have less energy contained in them than triple? If so, you're on your way. You can go ahead and move on.